presentation for our introduction of our research. And title is chiral symmetry breaking transition and I'm from Keio University from Japan, and this year is a celebration of 150th anniversary. So, at first, I may talk a little bit far away from origins of chirality, but biorhythms are ubiquitous in nature. When you see the picture of this tiger, not only tiger, but also zebrafish, spatial periodic patterns are observed in the surface of animal body. So this kind of spatial biorhythms are ubiquitous in nature. And of course, not only the spatial periodic patterns, but also temporal periodic patterns are observed in cell cycle, circadian rhythms, and pulsations. And so spatial periodic biorhythms and temporal periodic biorhythms are ubiquitous in nature. So the first question is, are these biorhythms phenomena seen only in life? It looks like a violation of the second law of thermodynamics. But when you understand the concept of dissipative structure, self-organization of in non-equilibrium system, these similar phenomena can be generated in chemical reaction. And this is the famous reaction called Berezov-Zabotinsky reaction. When you see the color of the solution, sometimes red and sometimes blue. And this reaction's solution contains iron. So when it has blue color, reduced iron is more than oxidized iron. And when the color is red, oxidized iron is more than the reduced iron. So it is chemical oscillations. And first chemical oscillation was found in 1921, but everybody doesn't believe this Bray reaction can generate chemical oscillation because it looks like a violation of the second law of thermodynamics. And more than 30 years has passed. Berezov-Zabotinsky reaction was found in former Soviet Union in the 1950s. But again, this reaction, most of the researchers don't believe this reaction can generate chemical oscillation. But the concept called brassolator was developed in, this is 1968 in Prigozhin's group. Why this chemical oscillation can be generated can be explained theoretically. And this is a concept of brassolator. When higher chemical potential starting compound is flow into the system, and this kind of reaction is performed, and final product D and E, that is lowest chemical potential product, is flow out of the system, and the concentration of intermediate compound X and Y can be represented by these two equations. And by analyzing the brassolator, it is a set of two kinetic equations. This can generate chemical oscillation. And this is the reaction mechanism of Berezov-Zabotinsky reaction. And this reaction is an oxidation of these two malonic acid and bromomalonic acid by bromate ion. So you can understand this is very similar to our life system. Life can take higher chemical potential organic compound by meal, then take that is same as this organic compound. And also, you take oxygen by breathing. So this is correspond to the oxygen. So, and during the oxidation of this compound by this oxidizing agent, product is generated. So almost after the compression of the Brod-Zabuzinski reaction, it is more like a soda, soda because it contains much carbon dioxide, and it has yellow color. So isn't that taste good? But it isn't taste good, but it looks like a soda. And spatial pattern formation. For modeling, Alan Turing developed model in 1950s, and it takes 40 years to generate Turing pattern by chemical reaction, and this work was succeeded in 1990s, and this is Turing pattern developed by this French group. And first Turing model is like this. Starting compound A is transferred to final product B. During this process, intermediate X and Y can be generated. And in this case, unlike the Brasseretter, we have to think about concentration distribution in space. So kinetic model is not an ordinary differential equation, but partial differential equation, because concentration is a function not only the time but also the spatial dimension. And these two equations are reaction term and diffusion term. Each reaction diffusion equation, these three terms and these four terms are reaction term, and the final terms are diffusion term. So reaction diffusion equation. And Turing analyzed this system to find out that the fluctuation can grow to generate spatially periodic patterns. And after 50 years have passed, Turing pattern formulation was succeeded by CMA reaction by a French group in 1990. And CMA reaction generate iodide ion, and iodide ion acts as an activator. So if this CMA reaction is performed in the presence of starch, starch reacted with iodide ion to show blue color. That's why this kind of blue, a little bit hard to see if you cross the
Yes, sure. That's okay.
Thank you. Blue part and white part are generated in the starch solution. In the blue part, iodide ion concentration is higher than the blue part. So this kind of spatially periodic patterns are spontaneously generated in the solution system. And Ilya Prigozhin got a Nobel Prize in chemistry in 1977. And he explained those periodic temporal patterns and periodic spatial patterns are not a violation of the second law of thermodynamics. He proposed the idea called dissipative structure to explain why this pattern formation are not a violation of the second law of thermodynamics. And this is a basic concept of self-organization in non-equilibrium system, that is dissipative structure. Please think about how you live. What is life? If one system should be life, make life, energy or high chemical potential matter should continuously flow into the system. You take meal, you take oxygen, and by reaction, diffusion, heat conduction, you make lowest chemical potential product, and you throw away those lowest chemical potential matter. So, and reaction, diffusion, heat conduction is irreversible and dissipative process. It always generates entropy. And if there's no flow like this, this irreversible dissipative process collapse fluctuation to make the system into equilibrium condition. But in the presence of this flow, this irreversible process can make fluctuation grow to like self-organized state. That is chemical oscillation, pattern formation, and also chiral symmetry breaking can be possible if this system is open to the outer environment. And of course, sorry, there are some Japanese, but chiral asymmetry. Of course, everybody knows in this room what chiral asymmetry is. This is a molecular structure of alanine, and this is a molecular structure of thalidomide. And when you prepare those chiral material by ordinary chemical reaction, both enantiomers are undoubtedly generated. But you know that in the life, amino acid is dominated by L form, and sugars are dominated by D form. And I lost one slide. And I worked with Guy, drip conductivity for 10 years. And he developed the model in 1985, so it is about 30 years ago. He regarded generation of homochiral state is due to the chiral symmetry breaking transition. That is one example of dissipative structure. In his model, starting compound S and T is flow into the system. Then S and T react with each other to generate chiral intermediate XL and XT. And also, not only this normal reaction, but also chirally autocatalytic reaction. In this case, XL catalyzed the reaction to generate XL, and XT act as a catalyst for generation of XT. And XL and XT form a final product, that is lowest chemical potential product. And this P is thrown away from the system. And he analyzed the model to find out that if concentration starting compound S and T exceeds some critical value, this racemic state alpha is a proportional to the enantiomer excess. So if starting compound concentration exceeds this critical value, racemic state is unstable to fluctuation, then homochiral state is generated in this model. And so we have worked together to realize real chemical system to generate chiral asymmetry by this model. And first, we have analyzed the crystallization system. And this is a compound called binaftyl. And binaftyl has axis chirality. Unlike the amino acid, this has chiral axis. This naphthyl and naphthyl connect with each other. So this and this is an enantiomer with each other. So this binaftyl crystallized in two forms. And racemic crystal has a melting point of 145 degrees, and chiral crystal has a melting point of 158 degrees. So if crystallization is performed under the temperature of this temperature, but above 145 degrees, chiral crystals are generated. But many crystals are generated at the same time. So if you don't start a crystallization system, the enantiomer excess of the crystal generated by this crystallization is centered at around 0. But when you store the crystallization system, in each run, only S enantiomer crystal or only R enantiomer crystals are generated. That is due to the secondary nucleation. Because once first chiral S crystals is generated, in the presence of storing agitation, it forms more and more secondary nuclei. And secondary nuclei and primary nucleus has the same chirality. So finally, the state that crystal phase are dominated by one enantiomer. And of course, very rapid racemization is occurred in the molten state. So when S crystals are generated and transfer from R enantiomer to S enantiomer by racemization is generated. That's why this kind of thing has happened. If there's no this racemization, first racemization, usually crystal systems are a mixture of R crystals and S crystals. But in the presence of this rapid racemization, this kind of phenomena can be possible. So
that's then at the temperature between 145 and 158.
Yeah. If you decrease the temperature below 145, racemic crystals are generated, so you don't see this kind of phenomena. So, but when you didn't start a crystallization system, crystal phase are nucleated and grow like this. This is a picture taken from the top. There's a tube here, and there are tube here. In the bottom of the tube, 1,1 prime binary melt is on the bottom of the tube. Then you can see the crystallization system from the top. And you see the nucleation here and nucleation here. And both crystal phase grow like this. And nucleation here and nucleation here. And finally, those crystals are merged into one. So why, when you take out these crystals before merging, you can see a little bit interesting phenomena. So crystal growth system can be regarded as an open system because crystal phase is here and racemic melt is here. So under the supercooled condition, chemical potential of racemic melt is higher than the chiral crystal phase. So crystal growth front can be regarded as an open system, in which high chemical potential melt is flow into the system and transfer to the lower chemical potential crystal phase, then throw away from this moving window. And we check these small crystal phase, an enantiomer excess of these small crystal phases, and find out that these bifurcation phenomena, x-axis shows the bath temperature and y-axis shows the, sorry, a little bit unclear figure, but y-axis shows the enantiomer excess of each crystal phase taken up from the melt. And those enantiomer excess averaged around plus 60 or minus 60. So, and there's no size dependence. This x-axis shows the weight of each crystal phase taken up from the melt, and y-axis shows the enantiomer excess of each crystal phase, and it shows that the enantiomer excess doesn't size dependent. So it means that when crystal growth occurs, crystal growth from enantiomer excess of the crystal growth point kept almost constant. So we consider another model. Of course, contributed Nelson models cannot be applied to this system. So we we established another new model, and liquid phase go to a crystal phase. And maybe Dr. Prason will present one more details of this model. And we from this figure we propose this 4-variable kinetic model, and I worked with Dr. Prason when he was in Japan, and this kind of bifurcation diagrams can be observed by analyzing this model. Maybe during our study you may present more detail about this model. If we talk about this model, it takes about an hour. So. And but original contemporary Nelson's models think about chemical reaction. So we start to try to generate a chiral symmetry breaking transition by chemical reaction. And one candidate of this contributed Nelson's model is Sawai reaction. He will come here next week. And in 1955, about 10 years ago, Sawai and co-worker found that this reaction, that is a reaction of some kind of aldehyde with diisopropyl zinc to generate this compound. And he found that if final product having some levels of enantiomer excess was added to the reaction system, final product has more enantiomer excess, like this figure. And in I remember it was again 2002. Year 2002, American group find out that in the absence of any chiral compound in this reaction, spontaneous generation of chiral asymmetry can be possible by this Sawai's reaction. And that is same as like Sawai reaction, but in this case, no final product is having some kind of enantiomer excess was added in the reaction system. So this reaction generates, I forget. There's no real enantiomer excess, but if you see that this Jack's paper, what kind of level of enantiomer excess is generated by this reaction can be seen in this manuscript.
So you get either right or left.
Right or left. And after this paper and Sawai's original paper, many groups try to analyze the mechanism of Sawai's reaction. But recently, Green et al. He's a Russian, but he's in Japan, and reported very interesting phenomena for this Sawai reaction. And this x-axis, this figure, x-axis shows the concentration of final product added into the reaction system, and y-axis shows the enantiomer excess of the product obtained by the reaction. So if you don't add any final product in advance, enantiomer excess of the final product is fluctuates from run to run, like this. And when you add a very small amount of final product having a high enantiomer excess, only one type of enantiomer dominates the reaction system. And when you increase the concentration of final product, experimental results are very reproducible. And those fluctuations can be seen not only for this enantiomer excess, but also a relative reaction. Please watch this figure. This x-axis shows the time and y-axis shows the aldehyde starting compound concentration. In some run, reaction almost completed within 1500 seconds, 1500 seconds. So it means about 20 minutes is enough to complete the chemical reaction. But in some cases, this y-axis is 10,000. So after 3 hours, only 60% of the starting compound is consumed. And so this shows that Sawai reaction result are very randomly fluctuated. So what are the kind of this kind of fluctuated reaction?
Can you actually measure the growth rate? That is, if you look at the initial enantiomeric excess relative to the enantiomeric excess at later times, does this increase exponentially at first?
Yes. And in this case, this is not paper, so I don't know much about this result. But this is the result of no final product added condition.
So the enantiomeric excess is
actually, he told me that the enantiomeric excess, final product enantiomeric excess, and this reaction behavior doesn't have any relation. But he said he didn't repeat many reaction. That's why he said he is not so clear about the final about the relationship between this reaction behavior and the final product enantiomeric excess.
Yeah, not necessarily the final, but at later times before the system saturates.
During the reaction system.
Yeah.
Actually, this is monitored by NMR.
Yeah.
So he didn't monitor the change of enantiomeric excess during the reaction for this experiment.
I see.
And so actually, there are same kind of random event in clock reaction. It is called crazy clock. And Epstein and co-worker did some same work, this kind of work in about 20 years ago. And this reaction is a reaction of thiosulfate with chloride. And when you react thiosulfate with chloride, there are two kinds of reaction. One is generate OH minus, and the other generate H plus. So even though both reaction consume thiosulfate, this increase the pH of the reaction system, and this decrease the reaction pH of the reaction system. And when you did experiment by changing the rate of stirring, results are very different. So sorry that small character, but when the stirring rate is 760 RPM, reaction doesn't proceed so fast. But when you decrease the stirring rate from 760 to 620, reaction occurs proceed very fast. And when 500 RPM, reaction proceeds much faster than the other two.
So one more time, the top one was 500
Yeah,
RPM?
500 RPM. 500
For the top
RPM,
one?
Top one. 620 RPM for second one.
Yes.
And 760
Yes.
for the last one.
And for zero?
Zero, suddenly, suddenly reaction arrived at the final. And actually, this is not the one reaction. This is maybe average of hundreds of reactions. And each reaction is like this. In some cases, pH gradually increase, but sometimes cases pH suddenly decrease. And these two reaction system is dominated by this first reaction. But these phenomena can be observed if this second reaction dominates the whole system. And by the analysis of this reaction, this second reaction is strongly autocatalytic. The rate of this reaction is proportional to the product of square of concentration with plus and concentration chloride ion. So this first one is general reaction, but second one is very strongly autocatalytic. And so they think about the effect of imperfect mixing. So if local higher content of H plus phase is generated, second reaction dominate the small subsystem of the chemical reaction system. Then diffusion occurs from small part to the other part. Then surrounded part, at the surrounded part, concentration of H plus exceeds some critical level. Second strongly autocatalytic reaction dominate this surrounding place. And as a result, this kind of diffusion autocatalytic reaction and diffusion autocatalytic reaction dominate the whole system to make this type of clock phenomenon. And this is crazy clock because this generation of this clock phenomena is statistically fluctuating from turn to turn. And if you
starts to fluctuate, you say?
Yes,
or you mean the crashes?
In this for this one, this clock phenomena occurs within 3 minutes.
Yeah.
But for this 5 minutes and 8-9 minutes, and these two, no clock phenomena is observed. So that's why when you increase the rate of storing, this local buildup of highly autocatalytic subsystem is collapsed by the forced storing. That's why in the presence of higher rate of storing, the action is dominated by this first reaction. So the action proceeds very slow. But if you decrease the storing rate, sometimes first reaction dominates the whole system to increase the reaction rate. And if you stop the reaction, first reaction suddenly dominates the whole system to arrive at final state.
What was the difference between left and right?
This is each reaction's behavior, and this shows the average. So when you make the 700 RPM, you repeat it about 100 reactions, and in some cases, there. For example, I forget the scoring condition for this linear, but. This is the same condition. So in some cases, when this kind of phenomena is observed, after 10 minutes, almost all reactions are completed. But in this case, maybe 50% or 60% of the reactions, only 50 or 60% reactions are proceeded.
Is it exothermal, this reaction? There is a heat evolution in this reaction?
Sorry, I don't know much about the heat reaction, but temperatures are kept constant at 20 degrees. So I don't think it is strongly exothermic. So we have analyzed Sawai's reaction with he's one of my students, and he did some experiment to analyze the Sawai reaction. It's just a 1 year experiment, so his work was not of course completed, but maybe it's better. It is okay to give a casual.
Maybe there are questions before that. Anything so far?
When you melt the binaft, and you saw some seed on one part of the submarine, and another one of the pictures,
like this?
there was another seed,
Yes,
another part, which are not connected. And then, is the configuration the same or the chirality the same?
It is very random. Each those
They are independent, completely independent.
completely.
And when they connect, of course, then it is the same.
If you for example, this one connected with each other, enantiomer excess is of course subtotal of this.
But they are completely independent.
Yes, that's why those enantiomer excess of each crystal is almost 50% to 50%.
So they only had rings, never spirals, right?
Not spirals.
Why do these binactile becomes racemic below certain temperature?
Because racemic crystals, if the temperature is below 145, chemical potential of one racemic crystal is lower than the chiral crystal.
What do you mean by racemic and chiral crystal?
Racemic crystal mean
both types are merged together.
Amorphous, maybe, is another word.
Different kinds of crystals. Sometimes the crystals have a right and the left that are quickly crystallizing, or in the other case, you have only the right crystallizing together and only the left crystallizing. And depending on the temperature, sometimes it's the one that are not stable, or the other that is stable. Either you have the right same crystal.
Racemic compound is a crystal contain both R and S enantiomer. And chiral crystal contains only R enantiomer and S enantiomer.
Due to the kinetics?
No, not the kinetics.
Crystallization takes place faster, and then both R and S
yes.
crystals might be.
Yes, but these are the melting point. So thermodynamically, racemic crystals are stable if the temperature is 145 degrees. But of course, if the temperature is below even though temperature is below 145 degrees, sometimes chiral crystals dominate because, as you say, kinetic reason.
There are some old rules in the literature that it's not general, but in the racemic structure, the packing is a little bit better. And the density of is a little bit higher. Then it is maybe one reason that there are many more cases of racemic crystal than conglomerates.
It depends on the molecule. It depends on molecule. Sometimes, of course, chiral crystal has lower temperature, lower melting point.
What do you mean? Normally, you mean, or what do you mean?
It depends on molecule.
Depends on what?
In this case, binactile. In the case of binactile, chiral crystal has higher melting point. But for example, if it is binactol, racemic crystals melting point is higher. So if it
excuse me, but higher melting temperature means that it is more stable. It is more stable than the racemic one. No? If the crystal is stable, then it stays longer. Higher temperature.
At 158 degree, racemic crystal, of course, will melt.
but it stays there.
The difference.
Below 500, 155, 58 degrees.
So, if you...
Exists, but the racemic already melts.
Yes. But
that means racemic is unstable.
Actually, when you... if you have a racemic crystal, and when you heat it up, and at 45 degree, it once melt, but transfer to chiral crystal. So, and finally, if you increase the temperature above 158, it melts. And those kind of polymorphs are very ubiquitous in, triglyceride or something like that. If when in summer, your chocolate is melted down, and when you put it in the refrigerator, tastes very bad because polymorph of the triglyceride is very different from the initial one.
Yeah, so it means the chiral one is more stable.
It depends on the conditions. You have at 145 degrees, you have a solid phase transition. At 158, you have a solid liquid phase transition. So below 145, it's the racemic crystal that is the most stable. Between 145 and 158, it's the chiral crystals that are more stable. And above 158 is the liquid that is more stable.
And once you obtain chiral crystal, maybe at around 150 degree, and if you decrease the temperature below 145 degree, it is kinetically stable because solid to solid transition is kinetically very impossible, and so that's why you get chiral crystal.
So at 145, you said there's a solid to liquid.
At 145 is solid. If you look at the first diagram,
oh, solid to solid. Yeah, sorry.
Two different solid phases.
Yeah.
But of course, kinetically, if you just rise the racemic crystals above 148 but 158, you won't observe the spontaneous transformation of the solid because it's kinetically very slow to observe transformation of one crystal to another phase.
Yes. Good. Any other?
So this is the rare case. Usually,
it's the other way around,
70% of the organic compound, racemic crystal has higher.
Yes. And actually, this is commercially very usefulness compound. Binoctol can be used as a raw material for chiral catalyst. So if you can obtain homochiral state of binoctol by just storing the calculation system, you can be rich.
And this packing argument applies now to which case? To this case or the other case?
No.
To the more general case?
No, in the other case. This is a special case.
Oh, I see. So then you break up the packing, the tighter packing, at the first transition when the chiral becomes unstable, and then you go to racemic packing, which is more loose. Yeah, that's understanding. Yeah, okay. So if you want to continue then? You need just this much. With the new computer, what is that? That's it, yes. Good. Good.
He worked in a laboratory for a year to analyze the mechanisms of isolation.
Mm-hmm. Okay. Yeah.
It is, as I told you, it is not completed research. So.
Mm-hmm.
Cutting which? So now I'm going to make a presentation. The title is Analysis of the Mechanism of Spontaneous Generation of Chiral Asymmetry in SWI Reaction. As everybody knows how home chiral states have been generated in nature is not yet to receive a clear explanation. As Mr. Asakura explained, in 1985, Condeplier et al. Suggested the kinetic model like this figure 1. In this model, certain compounds are supplied from the outer environment, and the products are discharged to the outer environment. And the system like this is called open system. And Condeplier et al. Supports the generation of homochirality was the spontaneous chiral symmetry breaking as dissipative structure in open system. As we can see from figure 2, they reported that in this model fluctuation blue and homochiral states were generated when the product of S and T reached the critical value. But this is just a theoretical model, and this phenomenon is not realized in real chemical reactions. In 1995, SWI et al. Discovered the alkylation reaction of pyrimidine aldehyde with diisopropyl zinc, shown figure 3. It is reported that in SWI reaction, when the product is added before the reaction, the product with the same chirality as additive is preferentially produced. And when the product is not added, enantiomeric excess is spontaneously generated. If this SWI reaction proceeds in open system, spontaneous chiral symmetry breaking may be realized like Condeplier model. In 2005, Grignev et al. Published an article about the SWI reaction and reported the unexpected reaction behavior. Figure 4 represents the measured enantiomeric excess by SWI reaction, and this part is the results when the product was not added. And you can see there is broad distribution of enantiomeric excess.
So what? So on the abscissa you have the catalyst.
Yes.
Which catalyst is that?
This is
product.
product.
It's the same as a product.
Yes. But initially you have nothing, right? I thought.
In the case of zero, nothing is added.
Yes. Oh, I see. And then you get. Right. Yes. Then you get a large variation, plus or minus. Yes, understand. Yeah, of course. And it has always positive access, enantiomeric excess, the catalyst. So in other words, at zero, yes, that's what he said. You produce also enantiomeric excess, but then of the opposite handedness in 50% of the cases. Yeah.
And figure 5 on the right side indicates the progress of the reaction when the product was not added. Although upper and bottom experiments were conducted in almost the same experimental conditions, in case of the upper experiment, reaction proceeded to only 60% after 4 hours. On the other hand, in case of the bottom experiment, the reaction was almost completed only 25 minutes after the outset of the reaction. In brief, behavior of the reaction varies considerably in every run. From the background like this, I proceeded the research to analyze the mechanism of Swire reaction.
I don't understand. What are the conditions for the two curves? What is the difference?
Same reaction condition.
Why they are?
That's why very unexpected phenomenon. Even though the reaction conditions are same, in some cases, like only 6% of the reaction is completed after 4 hours. But in some run, just 25 minutes is enough.
Just by chance.
Actually, we don't know the real mechanism why this kind of thing has happened. Like I showed you, Clark reaction generated in the same reaction.
This is for the zero.
Zero. Yes.
Can I just use a pointer, maybe? So here you find another few cases, of course, where it really stops at minus 10%, right?
Yes.
So that's not even an exception. This case corresponds maybe just to this case or something, right?
Green didn't tell me about Green said that there's no relation between the final enantiomeric excess with this behavior.
And this system, was that actually really open?
No, not closed.
So then it can, of course, simply suffocate. The system could basically suffocate. I mean, you produce too many of the P's, too many of the products, and then the system is full of P's, and you don't have any S&T's anymore, whatever that corresponds to in this model here. Yeah? So then it's dead.
Yes.
You can only work if it's open.
Maybe it's a little different. If you see that if you have not if you do not have observed this sudden acceleration, it means that you didn't have the reaction didn't really have started. In some cases, the autocatalytic reaction has time to process, and sometimes doesn't have time. It's really that it's not that you do not have enough reactants, but it just seems like in some time, for some reactions, the autocatalytic reaction can start, and sometimes it's slow to start, and maybe the reaction very slowly progress. And
but why? I mean,
This is a question.
No,
but
but
no,
yeah, but I mean,
I'm not sure that it
sure.
may be related to a closed system, because it's just that induction time are different, and so maybe sometimes the autocatalytic result, what we observe there, I think it's just sometimes the autocatalytic reactions, the autocatalytic mechanism can be started, and sometimes for some reason it doesn't.
Well, that doesn't seem like an explanation. I mean, it could still be, I would think, that if you arrange them perhaps spatially in a special way, so that you have that you grow locally right and left, they go to products P because of cross inhibition.
Yes,
so you produce a lot of products, and then the system is simply full, and you don't have any pure monomers anymore left.
That's right. Maybe this reaction is very complicated, and he will talk about precipitation, generation of precipitate during the reaction, and Dr. Kana also laid some paper about influence of precipitation, acidic amplification.
But maybe also there is a parameter difficult to control is the purity or quality of the isopropyl zinc. It is a commercially the reagent.
I think that GridNet is freshly synthesizing itself as isopropyl zinc. It's not a commercially one.
It is prepared.
Yeah.
Yes.
So it should be clean.
It's a complete. Maybe it's not one reagent, but a mixture of reagents. In the structure.
In this case, he prepared those spelling commas just before the reaction, and used those things at once and continuous reaction. So I don't think this is not usually in purity of spelling comma. Even though impurity, even if this impurity influence this reaction behavior, enantiomer excess should not be calculated from underlying.
I used the simplest compound one, pyrimidine 5-aldehyde, as a starting compound among several pyrimidine aldehydes. And point 2 is diisopropyl zinc, and compound 3, which is the product of soy reaction, is necessary for the analysis of the reaction behavior when the product is added. I synthesized these 3 compounds. First, I synthesized pyrimidine 5-aldehyde following the procedure in figure 7. After the synthesis, I confirmed the product was pure by NMR, and next I synthesized diisopropyl zinc following the procedure in figure 8. I obtained pure diisopropyl zinc by distillation. Then, as the additive of the soy reaction, I synthesized dimethyl 1-pyrimidine 1-propanol S isomer by with high EE by adding chiral catalyst following the procedure in figure 9. By HPLC analysis using a chiral column, I confirmed EE was 89% EE isomer was obtained. And And now I am going to explain the main subject of the research, the analysis of the reaction behavior. First, I analyzed the reaction changing the molar ratio of pyrimidine aldehyde to diisopropyl zinc when the product was not added. Keeping the concentration of aldehyde 66 millimolar, I changed diisopropyl zinc concentration. The molar ratio was from the left side 1 to 2, 1 to 3, 1 to 4. And when the molar ratio was 1 to 2, the yield was always around 10%, and the reaction rate was constant. But when the molar ratio was 1 to 3 and 1 to 4, although every run was conducted on the same condition, the behaviors of reaction varied in each experimental run, like the results of Gridneff. I observed the bifurcation of yield. As for enantiomeric excess, EE was almost 0% in every run. Then I am going to observe the initial stage of the 3 runs in which I obtained a high yield and which I analyzed in detail at the initial stage.
It was almost 0, you mean initially, in the last line? EE was almost 0, you say, in the last line of the text.
In every run, in this maybe 20 experiments? In total,
Yes.
in 20 experiments, in this case, every final product enantiomer is 0. And
Initially? No, finally.
Final. Because,
I see.
Because the product was not added in the reaction system in this case. And also, actually, I showed that other groups result that spontaneous generation kind of asymmetry is generated in Stoic reaction. But in those cases, it is not a simple pyrimidine aldehyde. It has some substituted group. So just a simple pyrimidine aldehyde reaction, other group didn't show any spontaneous generation of asymmetry.
I mean, but the plots don't show that then, or the plots show at least 10%, right?
Yield.
No?
So we need find the product or is observed.
Why does it stop at 10%?
The final product.
It's just how many final products you observe. So when you have this huge increasing, what we observed in the last one, you have this sudden acceleration of the reaction. In this,
I see. So
in this compound, you don't observe the spontaneous symmetry breaking that gives enantiomeric excess, but you can investigate the mechanism and you can see this sudden acceleration of weight, and it's what is investigated then.
I mean, does it mean that if you do it, if the yield is 20%, that in 20% of the cases you get 100% EE, and in the other cases you get 0? Or what does it mean?
In every case, only 0% EE. In every case, enantiomer excess is 0%.
you need seeding with this kind of product. You need to see results like enantiomer excess to observe a non-zero enantiomer excess.
Then explain again this curve. What does it mean? You get a yield of...
Y-axis yield.
Oh, I see. The yield is just the production, of course, of...
Nothing is added in this system.
Yeah, I see.
Nothing is added.
Okay, yeah, I understand that. Yeah, right.
No, nothing is added.
Okay, so what is then... and why don't you get EE here?
Because there's no equivalent distance.
And there's no autocatalysis, you mean?
Yeah.
Yeah.
But, as you can see, there are some autocatalytic behavior.
Yes, there's autocatalytic behavior, but not sufficient to be the observable enantiomer excess.
Yeah.
I don't understand. By respect to the previous papers, what is
Comes in the next one, yeah. Right.
no, what is published in the literature?
So
you have IEE.
Yes, in this case, different molecules are used. Most of the time. And in his case, in Greenleaf's case, this substitute groups are some other different. Some other materials are used for this reaction. R has maybe I forget the
triple bond.
Yes, something. In this case, just simple H.
Okay.
That's why.
It is special.
Yes, that's Greenleaf's reaction. They use some kind special aldehyde derivative.
Okay.
So in that case, spontaneous generation kind of asymmetries observed. But in the case of just simple pyrimidaldehyde, no spontaneous generation. But if you add chiral product in advance, same enantiomer is generated.
In the returning case, what is the yield? How much yield does he obtain in the returning? Because you obtain only 10% of the yield, and that's very low. Certain cases you get 70, 60.
In his paper, no, he didn't mention about any yield. But
in a certain case, in the upper case, he obtains 60%.
Yes.
That's
Yes.
60% of
Yes.
yield. And in the other case, he has 100%.
Yeah, almost 100%.
So he has got rather high yield, and you have got only a very low yield, and that may be
the time is different, in his case, 4 hours was 30 minutes, and in his case, the reaction stopped at 30.
Around 1 hour.
1 hour. And also, rate of reaction is different because we use different starting compound.
Then I'm going to observe the initial stage of the free runs in which I obtained a high yield and which I analyzed in detail at the initial stage. And they were represented by figure 10. This part is the initial stage of the reaction. And I confirmed that the reaction rate was slow at the initial stage, and after that the reaction became rapid. And this is characteristic of autocatalysis reaction. And by the way, participants were generated during the reaction. So I investigated whether the precipitates included the product or not. By comparing the amount of product in mixture before filtered and after filtered, I found out that from 60 to 90% of product was generated as precipitates.
And still no EE, right?
No EE. In this case, in the absence of added kind of material, no EE was generated in every case.
But just when you were giving the yield, it was the total yield by HPLC? Okay. But if you have precipitate, it means that you were getting the whole batch and redissolving batch?
Yes, it is. He added some sodium carbonate solution, aqueous solution.
Oh, okay, to redissolve, and then you analyze.
Then extract to the ether.
Oh, okay, yes.
Ether.
Methyl acetate.
Extracted by then analyzed.
So when the reaction stopped at 10 or 20%, it may mean that maybe there was lots of other compounds that were formed, but you can't know what is. It's just because the reaction stopped because we don't know why. You don't know exactly what happens when it stops. It's reaction stopped or because.
Aldehyde itself remains.
Yes.
Okay, so it's some kind of poisoning of the reaction stops because.
I don't know if it's poisoning or not, but
poisoning some sort.
Some kind inhibition.
Yeah, there is an inhibition. It's an inhibition. It's not that no subcompound is formed.
No.
Okay.
And next, I analyze the reaction behavior when the product S isomer was added. To begin with, I analyze the reaction behavior when a little amount of product was added. The concentration of pyrimidine aldehyde was 66 millimolar, and the molar ratio of the aldehyde to diisopropyl zinc was 1 to 2. And the concentration of the added product was 0.1 millimolar and 1.0 millimolar. The behavior was almost the same as the behavior before the addition of the product. Next, I increased the amount of added product. The concentration of added product was 13.2 millimolar. The reaction proceeded rapidly and yield was slightly increased. Then when the molar ratio was 1 to 3 and the concentration of added product was 30.2 millimolar, the reaction proceeded rapidly and high yield was obtained. From these results, I confirmed that the product acted as a catalyst. I also analyzed the time course of EE when the product was added. When the concentration of pyrimidine aldehyde was 66 millimolar, and molar ratio of pyrimidine aldehyde to diisopropyl zinc was 1 to 2, and the concentration of added product was like this. EE was constant at 0%. Next, when the concentration of added product was increased, so this is the result was like this. I confirm that EE was discontinuously enhanced depending on the amount of added product. When molar ratio was 1 to 3, and the concentration of added product was 30.2 millimolar. The result was also like this. And this is the conclusion. In Swire reaction used pyrimidine 5 carboaldehyde, spontaneous generation of VE was not observed. When the product was not added, the results were not expected like the results of experiments by Brignev et al. From 60 to 90% of the product was generated as precipitates. And it was confirmed that the product acted as a catalyst. And that's all.
Mm-hmm. Yeah, thank you. Thanks to both of you. What do we learn from that?
When this product precipitates, is there, did you check if there is lots of products remaining? Is it possible that you have some kind of, if the precipitate is not efficient enough, you have still a high concentration of the product, so you can't act as a catalyst? But once you precipitate, you can't have this autocatalysis.
So, yeah. I don't know, precipitated product act as a catalyst or not.
Yeah, the precipitate can
occurs and removed from system, and it does not act as a catalyst. I can understand reaction stop.
Yeah.
And if precipitation is deterred and in the supersaturated concentrations, okay?
Yeah.
And if it acts as a catalyst, I can understand why this kind of SCX are generated. But it is very hard to monitor by experiment.
Okay, yeah. It's not possible really just to try to monitor and to know what is in solution. But I don't know, it's just trying to understand what might happen there.
What is the solvent in all this chemistry?
Toluene.
With 13.2 millimolar of additives, you get yield shows different. That means one slide before. We with 13.2 milliliter, the above one or the lower one also. Only in that case, catalytic effect is shown. So that's the reason that the yield also becomes high. But in the other case, catalytic effect might be somehow killed and then yield is somewhere stopped, probably because of the precipitate.
Yeah, precipitation is one candidate why this kind of inhibition is generated. But I can say one of the candidates.
Precipitate means S-type and R-type coagulate each other.
Yes, in the case of, in these cases, from 60% to 90% of the product is generated as a precipitate. So, and not only the total product, but also few third of precipitates has zero enantiomers. So both enantiomers are coagulated with each other to generate precipitates.
So why is the formation of the formation of precipitates you really had only now in the end of the presented at the end of the talk? There was no precipitation occurring earlier in
when you add
in the standard
Even though 20% of the maybe 13.2 millimolar of product was added in advance, maybe because of the supersaturation, no precipitation was generated at the onset of the reaction. Of course, after the completion of the reaction, precipitations are observed. But at the onset of the reaction, even though 13.2 millimolar of product added, no precipitation was generated.
Do you know the possibility that there are some species which are mixed species between the product as alcoholate, zinc alcoholate, and diisopropyl zinc? Because the ratio of diisopropyl zinc to aldehyde is critical.
Yes, yes.
Why?
One reason is, I don't know why, but if isopropyl zinc form complex with final product, it's consumed by the formation, isopropyl zinc was consumed by the formation of the complex, and no reactant isopropyl zinc remain in solution. That's why I think these kind of stops, those kind of critical values are generated. But this is that assumption. No experimental analysis was done.
So,
Stir the reactor?
Yes.
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 Even though it is stirred, the precipitate forms.
Very small precipitation.
and the precipitates always pure.
In these cases, in acidic.
Always.
Acidic. And we didn't check the enantiomer excess of the precipitates when he added kind of product in advance.
Yeah.
We should check over it.
And the effect of, or at least in all those experiments where you did have precipitation, you found always a good tendency towards enantiomeric excess in solution. Is that right? In those experiments where you also had formation of precipitation, you always found in the solution a trend towards large enantiomeric excess.
No, in these cases, both precipitation solution has zero enantiomeric excess. And of course, we didn't check the result when we add chiral product in advance. In the absence of any chiral product, both precipitate phase and solution phase have zero enantiomeric excess. And of course, if we change the starting compound like green we may see different phenomena. But if we use this compound, no distribution in enantiomeric excess between crystal phase and.
So if you do add some chiral compounds in the beginning, you do find the evolution towards full enantiomeric excess. Would you?
Maybe. But
well, I mean, this sounds a little bit like a finite amplitude instability.
Yeah.
Is that what you think it is? It sounds a bit like a finite amplitude instability. So you would not go to either plus or minus for very small, naturally thermally occurring fluctuations. But once you give it enough of a kick, initially, it runs away.
Yes.
Yeah, but with this distance, the system is not selective enough so that you observe the symmetrical breaking just for statistical fluctuations. You need at least a little input. But in the green the molecule green used, it was selective enough because you have a larger group, so the molecule is more asymmetric. So this was sufficiently selective so that you can observe the symmetrical breaking even with statistical fluctuations. It's the idea.
Right. I mean, so a possibility would then be that you have a subcritical bifurcation in this case, as opposed to a supercritical bifurcation in the Gritnev case.
Mostly
Yeah, it shows the bifurcation curve again. Oh, no, there was another one. what I meant is you have the. No, I wanted to draw something. So suppose you have normally we have a bifurcation curve which in anti-numeric excess generates being generated once you exceed a certain control parameter and you reach -1 or +1. But of course you can have the so-called subcritical bifurcation, which means it goes the other way around. So the bifurcation curve really goes like this. That's a possibility, and
But why should you have this kind?
maybe there is no good reason as far as we can understand yet, but the behavior that you're describing looks as if this is what's going on.
Why should it look like that?
Because you don't find any instability if you just have initial perturbations in a very small window around 0. Once you have strong enough perturbations initially, you go to this curve here. Whereas here, even a very small excess gives you immediately to this point.
Yeah, but but there's no reason to have this kind of stuff.
Kinetics are very complicated. This kind of phenomena.
But
when we talk with each other, I saw some very basic model of this crystallization. And before your modification, it is uncontinuous change from racemic to homodirectic. After you modify your
Le grid 9, les ions compound, c'est malgré. C'est grid 9. They have a methyl group or hydrogen for the aldehyde?
Hydrogen.
The substrate is the same?
Substrate.
Yeah, the aldehyde.
In his case, it has different.
It is different. It is with methyl group here.
I forget the Leo. Maybe material was some complicated structure.
Why you took hydrogen?
Yes, methyl. Methyl or
classical.
Yes.
Why you decide to remove the methyl?
Yeah, because it is simple. The preparation is simple. This is his first year in the laboratory, so he's just reading it. So. Maybe next our school year started April, so next year we may change some other use other.
So what do you mean? What do you think should be done next? I mean, if you don't find the development of enantiomeric excess, full enantiomeric excess in this model,
also,
what would you do then to try and understand that?
When enantiomeric excess distribution in precipitate phase and solution phase should be monitored when adding chiral product in advance. Even chiral product is added in advance. Of course, reaction system is separated into solution phase and precipitate phase. And we didn't check the enantiomeric distribution in each phase. So we should check this distribution first.
I was actually also thinking that the fact of forming precipitates could lead, even in a closed system, to something effectively like an open system, as I think you said in your talk, in other connection.
Temporary is possible.
Yeah. So therefore, it's perhaps a really good thing to have that. But on the other hand, that's why I asked whether in those cases you do actually find enantiomeric excess, and the answer was no.
No.
But then that was maybe also for other reasons. So it may still be true then that and that the formation of precipitates effectively helps you in mimicking an open system to some extent.
Yeah.
What process, so you have to have dimers, I think.
Yes.
You check whether the dimer is
it is very hard to do. It is very it is very hard to monitor that kind of formation, and Canterbury Nelson's model consider about the dimer formation like this, but it should not be. It is okay X and XD form precipitate to throw away from the phase separated from the reactions. The kinetic behavior is the same. If it should not. It is necessary to be a dimer.
This is Canterbury Nelson's not a solar reaction.
Lucas,
Dimers is essential to be the open system. So.
No. If precipitation is generated, and if it doesn't precipitate, doesn't involve in the reaction system, it is more like a transient open system.
And then you should expect EE.
Yes, because
but it's the other way around. You get no EE. The precipitation is low. So this model might not explain the soil reaction.
Yeah, and also I think that we really have that actually. That's what we observe. But if you continually recycle the system, that if you take a small part of this and you input back, it was a singleton and have done, you always end up with the same enantiomer excess. I think it was maybe even with this kind of compounds. So what we obtain is that really we are there, but we actually we are the enantiomer excess should be this sigmoidal evolution. Okay, but actually, so if it starts really from zero, it starts to slightly augment, but because there is this strange mechanism, the reaction stops, and we do not have any compound, so we just make a very, very slight, but we can't observe it. But if you put back this fluctuation, put back in the system back, and then we continue to have this exponential growth, and we perform like that, it ends up to have the bifurcation. So we really have this very simple bifurcation pattern. But what is observed is, because the stereoactivity is not lost, is not the initial exponential growth is very slow, so you still at the beginning and still see zero. And because of the reaction, there is it's finite, it's a closed system, and then the reaction stops before the system has time to reach a steady state. So it's really this kind of stuff, but okay, we have to. The reaction stops before completion. I think it's what is the idea.
Stops before completion, but I thought it doesn't even get started. Sorry, maybe I missed that.
But there is some kind of some yield. It stops at the 25% 10 or 20% yield. So it starts.
Okay.
But, so it starts, but it stops before it's really time to arrive somewhere. But I think maybe with this kind, it was a singleton experiment. If you take back what was a small part of what was finally obtained and use it for seeding another experiment, and perform that several times, at the end you finish, you end up with one enantiomer excess.
Yes, exactly.
So if you do that, it means that actually it's not exactly zero, but a very tiny enantiomer excess that is obtained, but too tiny to be observed.
Yes.
So I think that, there should be this implication, but okay, there's a reaction for some reasons in the mechanism that we don't know. It starts, and the autocatalytic process don't really have time to be performed so that you can observe it. That's all.
But wouldn't you then agree that the real problem is really that the system is closed? If you were able to emulate something like an open system by using the product in the next experiment and so forth, having a sequence of such experiments,
but the
then you would have an open system, and then you would, as you said, reach 100%.
Yeah, but the proposal is not to obtain this high enantiomeric excess, it's to understand the mechanism and to understand what happens.
Yeah. Yes.
So I think that's...
It's still valid to do such an experiment, you mean, yes, of course.
So we know that if you perform this recycling, it works at the
end.
Yeah. Okay, it seems to be very complex inside, and then of course you can understand why.
Could there be actually in any of these cases a fact that the system is never perfectly mixed, and so that there's spatial segregation going on?
There's a possibility, but
what's the spatial extent of the system, and what are the flows?
トータルの大きさ、何ミリって
領域は20 1 point and 5 milli
is it diffusion control or is it
1.5 ミリ
Oh, I see. It's still,
トータル
yeah.
というのは
That's okay.
トータルどのぐらいの大きさなの？反応系の。
1.5 から2ぐらい、2ミリリットルぐらい。
販売するよ。
はいはい、20ミリリットル瞬間に。
20ミリリットル瞬間で、サンプリングやってる時
あ、するときは 0.1 ミリリットル。
そうなんだけど、ミリトータルだよ。イソトロプジンク何ミリ
で、0.3
あれそうもっと大きいのだったら。
容器は大きい。大きいですけど。
トルエンは
トルエンは1くらいです。
several milliliter of reaction systems he used.
Several millimeters of what?
Several milliliter of reaction solutions used.
Yeah, okay, I see.
And it was strong.
Yeah.
So,
but there was always stirring.
It's and small, so it should be homogeneous.
Yeah. Okay. Good. Right. Maybe then time for lunch. Yeah, thanks very much again.